Hey everyone. Today we're tackling rates of change, topics 1.2 and 1.3 from AP Precalculus. So let's break it down quickly and clearly. So, what is rate of change? The rate of change essentially tells you how one quantity changes compared to another. So we can write down the average rate of change is equal to the change in output divided by the change in input. And you're going to see a general formula that's written kind of like this. Sometimes you might see change in y over change in x, but this is the formula that you're going to want to remember every time you want to calculate rate of change. F of b minus f of a divided by b minus a. And so you're going to be given an interval. Maybe they're going to ask you to calculate the rate of change from x equals 1 to x equals 2. So you'd plug in, 2 for b and 1 for a, and then the value at x equals 2 and the value at x equals 1 for f of b and f of a. So let's talk about average versus instantaneous rate of change. So an average rate of change measures the change over an interval. All right. So let's say this is x equals 3, and let's say this is the 5 mark. So that pink highlighted part of the graph is basically measuring the average rate of change from x equals 3 to x equals 5, from 3 to 5. Okay. Instantaneous rate of change, let's say we wanted to know the average rate of change right here at that point. So to calculate instantaneous rate of change, we can approximate it using really small intervals around that point. So maybe we can plug in, let's say we want to know the instantaneous rate of change at x equals 1. So we can plug in like 0.9, 1.1. So we can just plug in values around 1, and that'll be a really good tool for us to predict the instantaneous rate of change at that specific point. Let's talk about positive and negative rates, because you're going to see that. So if the average rate of change is positive, both quantities are going to move together. All right. And they either both increase or they both decrease. So here I have two example graphs on the side. So I just made this up, AP grade and time spent studying. Sometimes it doesn't always work like that, but here's a sample graph. Okay. So basically this graph is saying as one quantity increases, the other increases. As you spend more time studying, your AP grade increases, right? They both move together. They're both increasing. This one has a positive average rate of change. On the other side, we have a different graph. And this time, maybe it's a football in the air, a basketball in the air after coming out of the net, something like that, or the hoop. So you have the height of the ball, and it starts off high, and it is falling towards the ground. So as time keeps moving on, the ball is dropping towards the ground. So yes, time is increasing, but the other one decreases. So that's another rule you're going to want to remember. If it's a negative rate of change, one increases, see, time is increasing, but the other decreases. The height of the ball is decreasing. Okay. Let's move on to how to compare rates at two different points. So if you want to compare rates at two different points, you can calculate the average rate of change near each point. So let's say you want to calculate the average rate of change. If you're given like 3, 1, and then the other point is like 5, 8. You can calculate the average rate of change at those two different points using values close by, as we talked about for instantaneous rate of change, and then you can just compare the rates of change. So whichever one has a bigger value is going to be increasing at a faster rate, smaller value increasing at a slower rate, or decreasing, if it's a negative value. Okay. Let's talk about linear functions. So for linear functions, the average rate of change is constant over any interval, right? Doesn't matter the length of the interval. You can make the interval like 100 x values long, right? And you're still going to get the same number. So no matter what 2 points you pick, where on the graph you pick, you're always going to have the same average rate of change. So let's calculate this. Here we have an example problem. Find the average rate of change for f of x equals 2x minus 7 from x equals 3 to x equals 6. So some of you watching might already know the average rate of change, but just in case you don't, we're going to plug this in. So let's find f of a first, which is, it doesn't matter what order you do it, and you can do 3 first. So let's find f of 3. So we have 2 times 3 minus 7. So what's 2 times 3? That's 6 minus 7 is -1. Okay. And now we're going to have f of 6, which is 2 times 6. Or sorry, let me write that down. 2 times 6, which is 12 minus 7. What's 12 minus 7? That is 5. Okay. So now, let's say that this is A and this is B. And our equation from earlier, our formula from earlier was f of B minus f of A divided by B minus A. So if this is our B value and this is our A value, let's plug that in. So we have f of B, which we got was 5, minus -1, which is f of A, and that's going to be divided by B minus A, so 6 minus 3. Okay, now let's solve this out. 5 minus a -1, that's going to become 5 plus 1, which is 6, divided by 3. 6 minus 3 is 3. 6 divided by 3 is 2. So our average rate of change is 2 over that given interval. But that's, since it's a linear function, that's going to be the same no matter what points we pick. We could have picked 3 and like 200 as the other x value, and you're still going to get 2. And notice how this 2 right here comes right from here. The slope. The slope is the average rate of change. So we're already given 2 up there. So honestly, if you really didn't want to calculate anything, you can just look at that and be like, oh, the average rate of change is 2. It says right there. That's the slope of the graph. That's how you can find that out for linear functions. Now let's talk about quadratic functions. So here I kind of squished this a little bit. So we're gonna have to work up here and use some of the space from the last problem. So for quadratic functions, the rate is not going to be constant, because recall a quadratic function looks kind of like this, and that's not really a straight line, right? It's not changing at a constant rate. This slope right here, you know, as the graph is kind of turning around over here, it's getting flatter out. That slope's going to have a, you know, less magnitude than up here, because this is coming down steep, right? Much steeper up there, so the slope is going to have a bigger magnitude. So for quadratics over here, note that the rate of change is not constant, but the change in rate is constant. So we're going to talk about that a little bit later, but we have an example problem over here. X squared minus 3x. So we're just going to do the same thing. We can use the same formula. We're going to plug in g of 1. And that's going to be 1 squared minus 3 times 1. Okay, let's solve that out. That's going to be, what's 1 squared? That's 1 minus 3 times 1. That's 1 minus 3. That's -2. All right. And then now g of, let's find the other one, g of 4. That's going to be 4 squared minus 3 times 4. Okay, what's 4 squared? That's 16 minus 3 times 4, which is 12. That's 4. Okay, same formula from earlier. F of B minus f of A divided by B minus A. We're going to do the same exact thing. So our b value, we're just going to do that and that. I like picking the bigger number as the b value, the bigger x value, so that we don't end up, messing with negatives. So our b was, this is a, this is b, that was 4 minus -2 divided by 4 minus 1. Okay, cool. What's 4 minus -2? That's 6 divided by 4 minus 1. That's 3, 2. So we got the same. This problem actually ended up being the same average rate of change as the linear one from earlier. But if you were to pick another set of different points, well, I guess I could just said the same thing twice. If you picked another set of points, you'd get a different answer. Okay. Let's talk about concavity. This is going to be important for AP. So, concave up and concave down, right? And you might be asked to find concavity from a table of values or a graph. Okay, let's talk about this. When the average rate of change is increasing, it is going to be concave up. When the average rate of change is decreasing, it's going to be concave down. So let's look at the first graph over here. We have a linear graph. Is the average rate of change increasing or decreasing? Well, this is the linear graph. The graph is just a straight line. And we know from linear functions that the rate of change is constant over any interval. So the rate of change is not going to be increasing or decreasing. So this actually has no concavity. Okay. Let's do some blue, actually. Okay. So it's going to have no concavity. Now, what about this one? If we look at the tangent lines of this graph, tangent lines are basically like the straight lines that come off the graph. Notice how the slope down here is kind of like this, right? It's kind of a flat slope, right? So that's not going to have a really big value. But notice how as the graph goes up here, the slope is now going like this. So our slope is increasing, and the slope is average rate of change, right? So the average rate of change is increasing in this case. So that's going to be concave up. And as you know, as if our graph opens upwards, that's concave up. It makes a U shape, and that's basically the half of a U. Okay. Over here, concave, this one is going to be, notice how our slopes are actually, decently steep at the beginning, but now we're kind of flattening out as the graph goes this way. So as our slopes are decreasing in value, our average rate of change is decreasing. This is going to be concave down. And concave downs make a frown. And this graph is kind of going down like that. Okay. Now, you might be asked to determine concavity and function type from a table. So how do I do that? Okay. Well, these are, notice how on this side we have equal length input intervals. So as we go from 1 to 2, how is this changing? This is increasing by 2, right? We're going from 2 to 4. Okay, how about from here to here? 4 to 6, okay, that's 2 again. 6 to 8, that's 2 again. And 8 to 10, that's 2 again. So this function is linear, right? Because over any length interval, the average rate, notice how these are equal length intervals, right? But even if we go from 1 to 4, the average, it's still 2. If you want to calculate that out, that's going to be, what? 8 minus 2, that's 6. Divided by 4 minus 1, that's 3. 6 divided by 3 is 2. So you're still going to get 2 either way. So if we want to write that into a sentence, this is linear because over any length interval, the average rate of change remains constant. And what do we know about linear functions? They have no concavity. And that's because the average rate of change remains constant. Okay, what about the next one? So here we have consecutive equal length intervals again, right? Because we're going from 3, this is 3, blah, blah, so on. They're all 3 apart. Okay, but let's look at what we have in the table. 2 to 5, okay. So that's increasing by 3, right? But how do we determine average rate of change? That's the change in the y values over the change in x's, change in outputs over change in inputs. So the outputs, these are increasing by 3, and that's also being divided by 3, right? Because change in output is 3 over 3. Okay. Let's look at the next one. That's 5 over 3, right? Because they're increasing by 5, still dividing by 3. The next one is going to be, now we're going by 7. Still, the inputs are over 3. And what's the difference between that? That is 9. We're increasing by 9 over 3. So now, let's talk about the value of these. So, what do we notice about these? These are all different, right? Our average rate of change is increasing over all those intervals. So this is actually going to be quadratic. Because over equal length input values, because these are all spaced 3 apart, right? So over equal length input values, the average rate of change, and this is something that you ought to pay attention to. How are these separated? How do you get from 3 over 3 to 5 over 3? You add 2/3, right? How do you get from 5 over 3 to 7/3? You add 2/3. How do you get from 7/3 to 9/3? You add 2/3. Notice how the change in the average rates of change are linear, right? That's constant, right? So that's how you identify a quadratic. So this table of values depicts a quadratic function because over equal length input values, the average rate of change is linear, right? And what's the concavity? Concave up, because if we just look over here at how our average rate of change are changing, they're increasing because the average rate of change over equal length intervals is increasing. And that basically sums up AP Topics 1.2 and 1.3. So here's the key things that you need to know about. Average rate of change is the change between 2 points. Instantaneous rate is a change at 1 point, and you approximate it using tiny intervals that are nearby. Linear functions have a constant rate of change, and quadratic functions, they have a rate of change that doesn't stay the same, but it changes, but the actual rates change in a regular, steady way, as we saw earlier in that table. If you look at equal length intervals, the change in rates follows a linear pattern. And concavity is determined based on how average rates of change.